Hi, so this is my video on surface integrals. So surface integrals are a lot like line integrals, except that the integration is done not along a curve, but along a surface. We did parameterized surface in the last lesson. So what you are trying to do is to perform an integral where the function which is defined is integrated along a surface. So remember, instead of a curve, now we are integrating along a surface, and that surface is actually parameterized by two parameters, u and v. So what happens is right now, let's look at, so we have the parameters u and v, which actually we have a u parameter and a v parameter, which in turn actually defines the surface. And then what happens is the function is actually integrated across the surface. So the function is somewhere else. So what we are doing is, this is the domain for the function, not this. So that's very important. This is the parameterization, right? This is the domain actually which parameterizes the surface. The surface is the domain for the function. So, and then the function is defined as we all know, it's a limit like a Riemann sum. And when you look at the Riemann sum, how do we take the Riemann sum? When we did in Calc 1, when we did Riemann sums, we took intervals, right? Okay. But right now, the Riemann sum is taken over, like we had those, we divided the interval into, in Calc 1, we divided the one-dimensional interval into pieces. But now what we have is a two-dimensional interval. So what we are going to do is we are going to divide them into parallelograms type of things right here. Okay. And so what happens is this. So what we do is this becomes like the width, and the height is actually the value of the function here. You can say that. And the area of this is the acts like the width. Okay, so this is like the height times the between the pre in a three-dimensional sense, right? Okay, and then of course you take the Riemann sum, and that's how you calculate the area. And but this function is actually, this is not very easy to handle right away like this. So what we are going to do is we are going to make it simplify, because we know that this parallelogram is actually mapped by a rectangle in the basic parameterization. So the parameterization is u and v, and if we have a delta u and a delta v, that's the one that actually maps to this parallelogram, as we saw in the section where we calculated the area of a surface, right? So when we use that, this integral actually reduces to this. So in the end, the surface integral is defined as this. Okay, so what we do is we calculate that area of the parallelogram, as we saw again in the section that we dealt with the surface area of a surface, right? The area of a surface, right? It's Ru, the derivative of the unit vector along the direction of u, cross product the derivative of the unit vector, the partial with respect to v, and we take the cross product and the magnitude, the absolute magnitude of that, and we take du dv, and that actually gives you that area of that parallelogram, and then that actually replaces this ds, and then really this is what we get. Okay, and so this is the formula. So once again, what we're trying to do is we want to integrate this function f, right, over this surface S. That's the idea. So this is a function f. I integrate this along the surface S. What we do is we parameterize the surface by u and v, which in turn, right, will parameterize x and y and z. So f will also get parameterized by u and v, and we replace the d big S by this base, the area of the parallelogram times, and then what the dA, and then we delta du delta v, and then what we do is we now integrate it along the parameterization. So basically, what happens is now we are back here. Okay, so it's easiest to explain this through an example. Okay, But before we go to an example, let's look at the situation. Let's look at a situation where the parameterization is pretty simple. We learned in the section that we dealt with parameterized surfaces, right? That if we can write the surface as z equals some function of x and y, there is an automatic parameterization where you have the first parameter is x, the second parameter is y, and the third parameter is z, which is actually f of x, y. So the parameters are x and y. So when that situation, this thing here actually becomes quite simple, and we will see why. For example, the uv becomes x and y, but this ru cross rv becomes very simple. And how do we do that? Because now let's look at ru. Now u is actually x, right? So ru is really rx. The partial of this with respect to x, what's that? The partial of x is 1, partial of y is 0, and partial of this is dabba is partial f over dabba, a partial x. Okay, so we have 1, 0, partial f over partial x, and that is your rx, the partial of r with respect to x. So now similarly, if you want to find the partial of r with respect to y, what do you get then? Well, then we take the partial with respect to y. This is 0, this is 1, this is 0, 1, and partial f or partial y. So 0, 1, partial f or partial y. Now, if you look at the cross product, we are trying to find, to simplify this, ru cross rv. So let's take the cross product ijk, and then ru is 1, 0, partial z or partial x. And a v is, v, this should be r. Well, it's actually x and y, so it doesn't matter because x is u and y is v. Okay, and so Rx cross Rv, which is the same as Ru cross Rv, which is the same as Rx cross Ry. What do we have? 1, 0, partial 0, partial x, 0, 1, partial 0, partial y. And when you do that, for let's take the first row. So this is, you hide this first row and first column, and we look at the determinant of this 2 by 2, and you get negative partial of 0, partial x, right? And definitely negative partial, so it's a negative there, right? Okay, and then we go to J, we hide the first row and the second column, and then we have partial of z with partial y, and there's a negative in front of that, of course. And then if you go to K, we just have 1. And now we take the magnitude of this vector, right? Okay, so there's a J here, which I forgot to write. It's the square of the partial of c with respect to x, square of the partial of c with respect to y, plus the square of 1, which is 1, and you take the square root of the whole thing. So that is your ru cross rv. So this is the junk which actually comes into this place. So this big place becomes very simple. So the surface integral actually becomes the integral over d, the region of fr of uv. F, so if our uv means xy, so because u is x and v is y, so fy uv, and the ru cross rv magnitude actually becomes this stuff over here. So this becomes quite a nice formula that you can use, and we will see how it is used in the next example that I'm giving. Thank you for watching this.